In this lab, we're going to walk through the architecture of how Linux containers work at a high level and dig down into the details. So I want to point out an important correction. If you Google Docker Linux containers architecture, something along those lines, you will get back a bunch of drawings that are incorrect. You will often see the containers running on top of Docker. You'll see like a blue box stretched sideways, and you'll see a bunch of containers running on top of Docker. And this is not how it actually technically works. So the Docker daemon and then the libraries that kick off the containerized processes all run side by side, really. And the Linux kernel is actually what does the scheduling of all the processes in a Linux system. So it's kind of misleading in my opinion, but it's just kind of how the industry formed and how people talk about it. But at the end of the day, from a compatibility perspective and from a technical perspective, all of the containers themselves actually run in Linux and are actually just Linux processes. So now let's kind of delve from the, build up from the bottom. Now that I've talked about, if you think about a Linux system, there are containerized processes and there are regular processes. And most of us are familiar with, your typical Unix daemons. And if you run ls or ps, those are all just regular processes, right? But what makes a containerized process, what do we mean by that? I mean, I'm going to try to put some boxes around that because it can mean a lot of things to a lot of people. But in the context of this class, I'm going to talk about it from the perspective of using a library like LXC or libcontainer or libvirt to create a special process that uses, three typical technologies in the Linux kernel. So namespaces, C groups, and SE Linux. And other than that, all these containerized processes use the exact same capabilities in the kernel. So the scheduling and the drivers for accessing file systems, et cetera, all of that functions just like a normal process. The main difference here is that we're creating the process through a library which wraps these kernel technologies and makes them easier to start, makes these containerized processes easier to start. Now, 3-4 years ago when Docker came into the picture, Linux containers already existed. And so you may say, well, why did they take off, right? Well, what Docker introduced was a local daemon that kind of sits there running on the box in user space, and a very simple CLI REST interface that allows you to, send very simple commands. So like Docker run to this API. And then this API talks to the Linux kernel and does all the things I mentioned in the last slide. And then finally, the Docker daemon, really added support for what we call container images and really made this idea of having a container image take off. And now we have what we call the Open Container Initiative, the OCI image format. So this OCI image format is an industry-neutral format that allows the entire industry to standardize on a container image that a lot of different software can use and consume. So this makes it really possible for you to essentially go out to Amazon and use one of their registries or, pull down Artifactory and use that as a registry. And so we now see an ecosystem forming of software vendors and cloud providers that can all standardize on this single OCI format and allow anybody to run the container with whatever software they want and, save them in whatever registry they want. But if you look at, this architecture, though, on the right, you'll see the Docker daemon kicks off the container D, which then fires off different instances of run C using lib's container to actually talks to the kernel and, again, fires up a new containerized process with different namespaces, C groups, and SE Linux. And then one of the things that I mentioned before was that this introduced container images, right? So one of the namespaces is a mount namespace. And so inside of this containerized process, it has a virtual view of the mounts on the Linux system. And one of these mounts happens to be the container image as the root file system. So I'll dig into it deeper later, but you need to understand that basically what Docker introduced was adding this container image and using a namespace to mount this container image so that it looked like you were virtually living in another Linux system. And so then the next level up, we talk about OpenShift and Kubernetes, and OpenShift essentially is Kubernetes. It's a Go binary like Kubernetes and uses a lot of the Kubernetes code. In fact, the Kubernetes is the upstream for OpenShift. But you'll notice here that it's really a party now, right? We have the Docker daemon container D run C calling libcontainer to talk to the to, the kernel. But now we also have an OpenShift node and an OpenShift master. And so the user comes in and interacts with a shell, right? And the user can interact with the OC command or the kube CTL command with the OpenShift master. The OpenShift master talks to the OpenShift node. The OpenShift node on any one of the nodes in your cluster then talks to Docker D, which talks to container D, which talks to run C, which then talks to the kernel. And so you can now see there's a lot of stages happening. But this is the actual architecture. So if you look, Docker D, container D, run C, OpenShift node, OpenShift master, etcd, all of these things live in the user space. They can also themselves be containerized processes, but I want you to understand they don't live in the kernel. Nothing is magical about these. These are just daemons and processes that essentially do things. And in this drawing, I tried to show that system D actually starts Docker D, OpenShift node, and OpenShift master, and then those three daemons start everything else. So now let's move on to kind of the architecture that we'll think about as we run through the lab. So in a distributed systems environment, you would have multiple masters and multiple nodes, right? And in front of the masters, you would have some kind of load balancer. When we do OpenShift, we typically use HA proxy as kind of a standard. And so you would load balance traffic to the API that you're talking to the OpenShift master. The OpenShift master then has an etcd database. That etcd database keeps track of all the OpenShift nodes and knows where to distribute the actual workloads to. And you don't have to worry about that as a user's perspective. The only thing you do is talk to the HA proxy, and everything else behind that happens for you. But in reality, the OpenShift master is keeping track of what's going on in the cluster and which nodes are up and which nodes are down, and if nodes die, and it knows how to reschedule workloads in different places. And then on each of the nodes, you'll see you have the Docker daemon, container D, and run C, firing off processes, containerized processes. Also in an OpenShift environment, the registry server lives somewhere out there in the cluster. It doesn't necessarily live on all the nodes, but it can live on some of the nodes. And in fact, you can have multiple registries if you really want. And then that registry has to be backed by some kind of persistent storage. Now, out of the box, the OpenShift installer saves data on the NFS storage, but we also support Gluster and all kinds of other things. So, and even using other types of block storage and things like that. So this is just a basic architecture, but I want you to understand that there's 2 points where the user can interact with a cluster, essentially. The user can either go to the load balancer, which will then kind of schedule everything and think in a very distributed systems kind of way. Or if you really need to troubleshoot something, you can actually connect to the Docker daemon. You could even SSH into a node somewhere in your cluster and then connect to the Docker daemon. Or you can configure the Docker daemon to connect to it remotely through a TCP socket or something like that, though it's not typically recommended. And then finally, one other piece of architecture, the community landscape. I think this is confusing for a lot of people. They don't understand exactly what is Docker, Moby, Kubernetes, OpenShift, OCI. They hear all these words. So I wanted to kind of show some of the more important parts of the communities and kind of how they interact. And so if you look, OpenShift is really made up of all these software projects, right? And then it is really influenced by and consumes from some of these other projects like the Open Container Initiative and the Cloud Native Computing Foundation. So, a couple of interesting pieces. In the Cloud Native Computing Foundation, there's a technical oversight committee, and they're pretty active. And they're always working on, kind of defining what Cloud Native is and thinking about how applications would work. And then also within the Cloud Native Computing Foundation, you have the Kubernetes project, which is the biggest project, and FluentD and Container D, which are projects that OpenShift consumes as upstreams. And then on the other side, you have the Open Container Initiative, which I mentioned, the OCI, images. Those are important. So the Open Container Initiative images there's a runtime spec, which is run C, is kind of the implementation of that runtime spec, and then the image spec, which defines what container images, a standard container image, how they're formatted. And again, I mentioned this enables a huge ecosystem of software to form around this, right? So if we can all standardize on this OCI image format and we use this runtime spec, we can, have a pretty good definition of what a container looks like at rest and when it's running. And then the rest of OpenShift, it's based on RHEL. It uses etcd. It consumes, from the upstream Docker Moby projects. Open vSwitch, Kibana. You can see there's a list, and then the main upstream project that really pulls all of the OpenShift stuff together is called Origin, and so I put that in there so that you understand that Origin is kind of the upstream for what we call OpenShift Container Platform, which is the downstream productized version of OpenShift. And then I could go into the weeds, but we also have OpenShift Online and OpenShift.io and a lot of other pieces parts, but I won't go deep into that. I just want you to understand how the actual community pieces fit together. I think that's an important piece of the architecture of containers, and kind of giving you confidence on what you can consume and what you can't, and what has future and what has legs, and kind of, giving yourself confidence.